Okay, so I think we'll get started. So yeah, so first I want to say that because of the bad weather last week, so we two classes. So we need to make up two classes, and the university asked me to the dates the university gave me to make up that those two classes are Saturdays. So which I think might not work for everyone. So what I have in my mind is that to just record two classes and post those two classes online, and you can watch it yourself. And if you have questions, you can just feel free to ask me. And I'm thinking that the topics, yeah, so the topics I'm thinking to, sorry. Okay, yeah, so the topics I'm thinking to record is the topics at the very end of this class, so which are those additional topics. Okay, so I will make recordings of maybe 2 or 3 additional topics in this module and put those topics online and you can watch yourself. Okay, so, but yeah, so I mean, any concerns or any questions on that? Or if you want me just to do the lectures on Saturday, I just want you to get some maybe thoughts or things from you. Yeah, so, okay. Yeah, so my current plan, right, yeah, I totally understand. Saturdays are actually not good for everyone. And yeah, okay, yeah, but I mean, if you have some concerns or questions, just feel free to let me know, and I will also send you an email later, maybe, to discuss this. Okay, so now let's let me see. Okay. Okay, so all right, so now let's just move back to our class. Okay, so for today, or starting from today, we will yeah, so one asks me, do I have any general test comments yet? No, I haven't graded yet. So I will try to finish grading by this weekend. So yeah, so we maybe can talk more about the test next week. Okay. Okay, so we have discussed like a lot of theories of the time series models. So we have discussed stationary, we have discussed like the autocovariance, cross covariance, autocorrelation, cross correlation. So we have discussed a lot of stuff. And all this stuff would help us to build up our autoregressive moving average model, which is the ARMA model. So for today's class, I will first give you an example of the ARMA model. And starting from there, we will move to the theory parts of this ARMA model to discuss more about this ARMA model. And after that, I want to show you more examples of applying the ARMA models to the real data. Okay, so this is an example. So this is an example is the temperature in the furnace as time passes. Okay, so so this is like the temperature plot, the time series plot of the temperature. So you can first easily see that this is not a white noise plot. So it is easy to see that the data, for example, the data is related to its previous data points. So it's definitely not a white noise data point. And if you cannot directly see it from like this raw data plot, you can just plot the ACF. And the ACF will tell you that this is not a station, this data has some correlations. Okay, so yeah, right, okay. I think the slides just give us the correlation. So the first plot here is temperature, which is the lag 1 temperature. And the second plot is the plot of the temperature versus the lag 2 temperature. And this is temperature versus lag 3 and temperature versus lag 4. So you can very easily see that the temperature versus lag 1 temperature has like a very strong correlation, I should say. Like this correlation gonna be 0.6 or 0.5 maybe. And the temperature versus the lag 2 temperature, there also has some correlation, but this correlation is not that strong, okay? And when we draw the plot of the temperature and the lag 3 temperature, you can see the correlation becomes weaker. And when you have like this temperature versus lag 4 temperature, it's basically there's not much correlations here, okay? So you can see that there's less and less correlation between observations further apart, okay? But yeah, and here's the ACF plot. It just captures like this serial correlation. So when the time lag is 1, we have a very strong correlation. Yeah, it's 0.7. And when we have like lag 2, then it's 0.3, and it just like becomes statistically insignificant after the time lag 2. Okay, so this, I mean, this three, like this raw data plot, the serial correlation plot, and this ACF plot just tell us that there are some correlations in the raw data set. Okay, and in order to model this temperature data, so we can use so we can use a ARMA model, okay? So which is autocorrelation moving average model. And the question here is that which ARMA model we want to use, okay? So do I want to only include 1 lag in the model, or do I want to include 2 lags in the model? Or how about including some white noises in the model? If you just look at like this ACF plot, then you might think that including like lag 1, or I mean 1 lag in the model might be appropriate. However, we actually want to do a more systematic analysis of the ACF plot, and we will also study the PACF plot and decide which model we want to use. And this is sometimes called the model identification. So we want to identify the right model that will fit the data, okay? And in the time series analysis, we will use the ACF and the PACF to decide which model we want to use, okay? Yeah, so we have discussed a lot about the ACF. So the ACF is the autocorrelation function. And I just show you this, and you can see that there's 1 lag or maybe 2 lags that are statistically significant, and all the other lags are not statistically significant. Okay, so now, and another tool that we will use to determine which model we want to use is this called the partial autocorrelation function, or sometimes called the PACF. Okay, so the PACF, the difference between the PACF and the ACF is that this PACF is a partial autocorrelation, or in other words, this is a conditional correlation, while the ACF is just the autocorrelation, or the unconditional correlation. Okay, and simply speaking, the PACF is that if you run a regression, say like ZT, with zt minus 1, zt like all the way to zt minus k, okay? Then the PACF or the lag k PACF is basically the coefficient of the zt minus k. So in this example, the PACF of this lag k is just this phi kk, okay? Okay, so so that's, yeah, a very simple definition. And the idea here is that because you have like this zt minus 1, zt minus 2, all the way to zt minus k minus 1. So that basically says that you condition on zt minus 1 all the way to zt minus 1 minus k, okay? And you find the correlation between zt and zt minus k. And that correlation can be captured by this phi kk. Okay, so this partial autocorrelation is just the autocorrelation between zt and zt minus k, conditioning on all the terms in between. Okay, so that's the partial autocorrelation. Okay, and similar to the ACF, the 95% confidence interval of this PACF is also 2 over the square root of t. So this is exactly the same as the ACF. Okay. Yeah, so okay. All right. Yeah, so okay, so before like checking this PACF plots, I think I want to maybe talk a little bit more about this PACF, I think, because I think yeah, that would be better. Okay, so let me switch to the whiteboard here. Okay, so for today's class, I will try to cover a lot actually for today's class. So so first, some additional explanations of the PACF, the partial autocorrelation function. So the PACF between xt and xt minus h is just a correlation between xt and xt minus h, conditional on all the data points between xt and xt minus h. Okay. So example. So the first order PACF is just equal to the first order ACF. The reason is very easy because there are basically no data points between xt and xt minus 1. So the first order PACF is just equal to the first order ACF. Okay. And the second order PACF is the covariance. So it's the covariance of xt and xt minus 2 conditional on xt minus 1. Okay, and because we are doing a correlation function, so we will like rescale it by the variance. Okay, so we rescale by the variance to obtain a autocorrelation function or the partial autocorrelation function. Okay. And the numerator can be just calculated by this. Okay, so this is a very standard covariance decomposition. So the covariance is equal to the expectation of the xt and xt minus 2 minus the conditional expectation of xt times the conditional expectation of xt minus 2. Okay, and here for the variance, it is just equal to xt squared So this is the second PACF, and the third PACF can be just computed in the same way. The only thing that you need to add here is that you not only need to conditional on xt minus 1, you also need to conditional on xt minus 2. Okay, yeah, and in regression, so if you want to use a simple regression, I mean a multiple regression model to capture the xt and xt, say xt minus 2, then all you need to do is just run a regression of xt and xt minus 1 and xt minus 2. The coefficient in front of xt minus 2 is just the autocorrelation or the partial autocorrelation between xt and xt minus 2. Okay. Okay. But here, this is like more general. So this is like the definition. You actually do not need a regression model to capture the relations between xt and xt minus 2. Okay. What the slide shows is just a special case of this. Okay, so I think I have a question here. Yeah, okay, sure. I can write out the third term. So it is a covariance between xt minus 3, xt minus 1, xt minus 2 over the variance of xt minus 2, 1 xt minus 2 over variance xt minus 3, xt minus 1, xt minus 2. Okay, so that's a third partial autocorrelation function. So it's the correlation between xt and xt minus 3, conditional on xt minus 1 and xt minus 2. Okay. Okay, so that's a little bit more additional explanations on the partial autocorrelation function. Okay, so now I think I want to move back to the slides and see what is the partial autocorrelation function in our data set. So here's the ACF. So the top plot is if, and the bottom plot is the partial autocorrelation function. So the partial autocorrelation function, you can see that's pretty much similar to the autocorrelation function, right? So the first definitely is exactly the same as the autocorrelation function, because this is what we just discussed. So the first order autocorrelation is equal to the second, it's equal to the first order partial autocorrelation. And the second order partial autocorrelation is statistically significant, obviously. And the second order autocorrelation is also like somewhat statistically significant. And the rest of the partial autocorrelation function is not statistically significant. Okay, and similarly, the rest of like this autocorrelation function is also not statistically significant. Okay, and also point out like this dotted lines here and this dotted lines here are the 95 confidence interval of the autocorrelation function and the partial autocorrelation function. Okay, so based on this, we can actually determine what model we want to use. Okay, so here's the table that we want to like memorize it or maybe have it in the cheat sheet. Okay, so this says that for the, so how to read this table? Okay, so if the model is an ARP model, okay, then the autocorrelation function has this property. So it has like a infinite damped exponentials or damped sine waves and tails off. Okay, and for the PACF, it is finite and it will cut off after p lags. Okay, so the key point here is that the PACF cut off after p lags, while the autocorrelation function just have like those damped sine waves. Okay. Right, so this PACF would be very informative. It will have you a ARP model, okay? And for the MAQ, the moving average model, which can be written in this way, the ACF now is finite and it will cut off after Q lags, okay? And the PACF now becomes infinite, okay? And it has damped exponentials or damped sine waves and tails off. Okay, so if you plot your ACF and the PACF, and if you find like your ACF plot cut off at after Q lags, and this PACF has like is infinite and has damped sine waves, then it will tell you this is an MAQ model. Okay. And for the ARMA-PQ, which is a combination of the ARP and MAQ model, this is like the properties of the ARMA-PQ. So the autocorrelation function, it is infinite damped sine waves and tails off. And for the partial autocorrelation function, it also has infinite damped sine waves and it tails off. So you can see that this ARMA-PQ, the ACF and the PACF are actually not very informative, right? So for the ARP, if we find like this partial autocorrelation function cut off at p lags, we know it is ARP. And if we find the autocorrelation function of a time series cut off after Q lags, then we know this is an MAQ model. However, if you find both of your ACF and the PACF tails off, you know that you have an ARMA model, but you actually do not know like what orders you will choose. So what P you will choose and what Q you will choose, okay? And in those situations, the things becomes tricky. And to decide which model you will choose, you only know that you will choose an ARMA model, but you do not know what P and what Q you will choose. And in that case, what you will do is that you will perform the model selection. So which is what we just discussed earlier. So you will check the significance of the coefficients. You will check the R square. You will check the AIC and the PIC. And also in this class, we will also talk that you will also check the residues plot. Okay, so you need to do all this analysis to determine what P and what Q you want for your ARMA model. Okay, so the ARMA model is actually tricky. However, the ARP and this MAQ model is very easy. You can just plot the ACF and the PACF and decide like which cutoff it is at, then you can determine whether it is ARP or whether it is an MAQ model. Okay, so now back to our plot. So this is a very, very good plot. So you can see for the ACF, it is infinite, and it has like a very clear sine waves. Okay, so the sine waves is like the sine and the cosine waves. Okay. And for the PACF, you can see that it cut off at leg number 2. So after leg number 2, all this PACF becomes statistically significant, statistically insignificant, and we do not find like those very clear sine waves. Okay, but I know some of you might not agree with this. You might say that this ACF plot has cut off at number 1, and this PACF has like this sine waves. Or you might think that both of this ACF and both of the ACF and this PACF has this like sine waves. So you might think that using a ARMA model might be appropriate. Yeah, but here, like the I mean, trust me or trust the textbook. So this is so by just looking at the ACF and the PACF, we think that a AR2 model would be appropriate. So the PACF cut off at leg number 2, and the ACF has this sine waves. Yeah, and I would just want to point out that in your real analysis, you actually want to do a lot of like model selection and decide like this AR2 is your chosen model or your preferred model. So for example, here you want to do a AR2 model. You also perhaps want to do a MA1 model, or you perhaps want to do a AR2 MA1, like ARMA12 model or ARMA21 model. And you want to do like all these model selections and decide that your AR2 model is the best model. Okay, but the textbook just, I think, use this AR2 model. It says that it has damped sine waves and it cuts off after leg 2. But in your real analysis, I really want you to do all those models and to run the model selections. I know like different people would have like different views on this ACF plots and this PACF plots. Okay. Okay, so any questions on like reading the ACF plot and the PACF plot and the relations between the ACF, PACF, and the ARMA model? We'll get back to this a lot like in this class. Okay, so first, any questions here? Okay, so if there's no questions, then let's think that the AR2 model is a model that we want to use. Okay, so then the next step is just to fit this model. And to fit this model is pretty simple. It is just like a linear regression, and the regression, like the explanatory variables are the 2 legs, ZT-1 and ZT-2. Okay. And here in this like regression, we actually include a constant. So this is, you can think of it as an AR2 with a drift. And this is basically the same as like this AR2 model without the drift. So I will explain later. The only difference is that like in this AR2 model, you do not like demean the data, but here, I mean, so, I'm sorry. So in this like AR2 model, you demean the data, but in this AR2 model with the drift, you do not need to demean the data. But the coefficient or the parameters of interest, this phi1 and phi2 we get from this AR1 or the AR1 with drift would be basically the same. So I will explain that later, maybe after finishing these slides. Okay. So you can see this is like the regression results we have. So the phi1 is about 0.98, and this phi2 is about negative 0.37. And this constant term is not that informative. It's like 615. But more importantly, we find that both the coefficients are statistically significant. So both the p-values are much, much smaller than 1% or 5%. And we can also get, I think this is a squared error. Those are, I mean, the variance of the squared error. Okay, so yeah, so this is like the regression. The regression results you have. Okay. Yeah, so we find that all the parameters estimates seem to be statistically significant, which is very good. Okay, and yeah, I think I want to make one point here. I think some people, this is a time series regression. So even though it is like a linear regression, the interpretation of this phi1, this interpretation of phi2 is very different from like the interpretation of a cross-sectional regression model. Okay, so why I say this? So suppose that if you want to interpret this phi2, okay, so in a cross-sectional model, the interpretation of this phi2 is that suppose we increase like zt minus 2, say by one unit, then this zt would increase by phi2, right? So that's and holding other things constant. So that's your interpretation of a regression model in the cross-sectional data. But here, that regression actually does not make any sense, because if you increase zt minus 2, your zt minus 1 would also increase. Right? So that means you can actually not hold other things constant. Okay, so an increase of zt minus 2 would affect zt by phi2 plus phi1 times like whatever changes on this zt minus 1. Okay, yeah, so you cannot have like a very simple explanation or a simple interpretation of this phi2. Okay, the phi2 is not necessarily the effect of zt minus 2 on zt. The effect of zt minus on zt not only goes into this phi2, but also goes into this part. Okay, yeah, so I mean here the interpretation is very different from the cross-sectional data. And I think based on this reason, people really do not like to interpret the coefficients here. Okay, so in other words, so maybe in your report or in your analysis, do not like try to interpret this coefficients. And if you want to interpret this coefficient, you want to be very careful. Okay, so the effect of zt minus 2 on zt has two channels, this phi2 and this phi1 times zt minus 1. Okay, so you need to be very careful. Okay, so all you need to talk about here is whether these coefficients are statistically significant or not. So do not try to, avoid try to interpret these coefficients. They do not make much sense here. Okay. All right, so this is the coefficients of the regression models. Okay, then we should consider whether the assumptions of the model based on it can be satisfied or not satisfied. Okay, right. I think yeah. So what's the assumption here? So the assumption here is that we are doing a AR2 regression. So it's a AR2 regression. That means that this regression gonna to be stationary, right? If it is not stationary, then it is not an AR2 model. And here, based on these coefficients, okay, so it's it's perhaps a little bit hard to see like from here whether this is stationary or not stationary, but I will discuss later that these coefficients would make this model a stationary model, so which I will discuss later. So that means this is a stationary AR2 model. So the assumptions based on this model satisfied. Okay, so which is so far so good. So we have all the coefficients significant, and we have like this is a stationary model. Okay, and the next things that we want to check is the residual analysis. So why we want to do this residual analysis, or what residuals we want to expect? So the residuals we want to expect is that we want these residuals to be a white noise, right? So because this is an AR2 model, so we know that this AR2 is that this ZT is related or is affected by ZT minus 1, ZT minus 2, and some white noise. Okay, so that means if we minus ZT and 1, ZT minus 1 and ZT minus 2 from ZT, then the rest of the part of the model, so which is this AT, should be a white noise. Okay, and we can easily use the ACF and the PACF to check whether our residuals is a white noise or not a white noise. Okay, so to do this, yeah, so we can, yeah, so this is basically what I just discussed. So if the model is appropriate and the parameters are properly estimated, then there should not be any autocorrelation left in the residuals when the model is taken out of the raw data. And the easiest way to check this is through ACF and the PACF. Okay, so here's the ACF plot and the PACF plot of the residuals, and you can see this is a very, very good plot. All the legs of the ACF and the PACF are statistically insignificant. Okay, and we do not see that much correlations across those legs. So this suggests that the ACF and and this suggests that this residue is a white noise residue, and which is good, which is the thing that we expect. Okay, so yeah, so from here we can see that the AR2 model we use is a very good model. It has statistically significant coefficients. It satisfies the stationary assumption, and more importantly, the residuals follows a white noise process, so which is very good. Okay, so so I think I have a question here. Graphically, does that show? Doesn't depend on time. No, just recall like the ACF of a white noise. So the ACF of white noise, I think, should be equal to 0, right? After lag 1, right? And after lag 0. So that's basically what this plot says, right? It satisfies the definition of the white noise. So it is insignificant, right? It is insignificant. So insignificant means it is not different from 0. So we can interpret it as 0. So that's insignificant means, right? Okay. And we know that the ACF of the white noise should be equal to 0. Okay. And this plot just shows this. It is insignificantly different from 0. That's what this plot says. And this is the same story for the PACF, for the partial autocorrelation function. Okay. Okay, any more questions? Okay, so this is like a standard example or a typical example of what I expect you to do in your analysis. I will make the steps later in the handwritten notes. Okay, so for now, let me switch to the handwritten notes and first make some comments on the model that are not shown in the slides. So some remarks. So the first remark I want to make is this. So in the slides, or it has like basically has two AR2 models. The first is ZT constant plus phi1 ZT minus 1, phi2 ZT minus 2 plus AT. Okay. Right, so this is the AR2 model with the drift. Okay, and this is like the Euro output you will get from either R or state. Okay, so the regression you have like always include this constant term. Okay, but you can definitely ask the software to not include the constants. Okay. But we know that the standard AR2 model should be like this. Let me. So this is a standard AR2 model. It's an AR2 model without the drift. And I want to show that these two models are basically the same if you run the regression. Okay. Why? So let's first have like this mu equal to the expectation of ZT. Okay. And because this is a stationary process, so we know that this mu does not depend on time. Okay. Okay, so now what we do is that we subtract this mu from both the left-hand side and the right-hand side of this AR2 model with a drift. No, I mean, no, this is not a good way to present this. Sorry. So let's do this. Okay. Let's do it in this way. That would make things easier. Okay, so and also now let's like this ZT delta, so which is so variables in the AR2 model equal to ZT, the raw data minus the mean. So this is like the demeaned data. Okay, so if this is setup, then what we have is this. So ZT delta, this is our AR2 model. Okay. And this is equal to ZT minus mu equal to phi1 ZT minus 1 minus mu plus phi2 ZT minus 2 minus mu plus AT. So this is just by setup, okay? And we can move mu to the right-hand side. And this would become mu minus phi1 mu minus phi2 mu plus and now let's call this part as constant. So this is now our AR2 with a drift. So this basically shows that the AR2 and the AR2 with the drift are basically the same model. The only difference is that the AR2 model is the deminked model, while the AR2 with the drift model is just like the raw data model. Okay. So I mean to summarize. So if you do not demean, then use AR2 with a drift. Okay. So if you do not do demean, and demean is this, then you can then you have to use AR2 with a drift. But if you actually do demean, then you can use AR2 model, or you can actually also use the AR2 with the drift model. So both of this model would be fine. If you demean, if you run an AR2 model, if you run AR2 with the drift model, the constant you got after demean is just equal to 0. You can check you can check yourself in R or in Stata. So if you demean the data, then the constant term you have gonna be equal to 0. Okay. So here is the summary. Okay. Yeah, and also I think this is a trick or a technique in the data analysis. Okay, so in the cross-sectional data, this basically says if you do not demean, then you have to use the regression with a constant. However, if you demean the data, then using a regression with a constant or without the constant would be equally fine. Okay, and that result also applies here in the time series analysis. So this is the first remark I want to make. The second remark I want to make is about like the example. Okay, so the coefficients of the example. So we have the P1, P2 equal to So for a AR2 model, if like there's 3 requirements on the coefficients satisfied, then the model is a stationary model. And I think you can check yourself that these 3 requirements actually satisfied in our estimates. Okay, so they suggest that our AR2 model is a stationary model. Okay, just recall we are doing an AR1 model, then all we need is the absolute value of the phi is less than 1. No, you have to need all of these 3 requirements to be satisfied. Okay, so you need all of these three requirements to be satisfied. Then this is a stationary AR model. Okay, and no, this is negative. Negative 0.37. Okay. So this is a very easy way to check whether your model is stationary or not stationary. And later, yeah, maybe today, if I have time, I will discuss like there's actually a general way to check whether your model is stationary or not stationary, like for in the sense of a AR model. We'll use something like the unit root check. Okay. Okay, so let me have another page. Third remarks, or maybe a summary of like the steps of a data analysis. So I want to make a summary of the data analysis. Okay, so step number one, we have the raw data. The first step is that to do EDA, the exploratory data analysis. Okay. And we have discussed a lot of the exploratory data analysis early. So you can smooth data to check stationary, to check seasonality. If it is not stationary, then the trend. Take logs to remove the heteroscedasticity, or maybe other ways. Okay. We will discuss how to address the seasonality later. Okay. So we will add like how to address seasonality later. So here is just, you know that the data can have seasonality. Okay, so this is your step number one, to do the exploratory data analysis. Okay, and the key of this stationary data analysis is that you want your data to be stationary, and you also want to check if your data has some seasonality pattern. Okay. You have stationary data. No, I mean it's not a stationary data. It's not good. You want to remove the trend. It's down. That's how it's. Okay. Step number two. Step number two actually has two parts. So part number one. So if you want to do auto model, so the auto model is basically like xt with xt minus 1, xt minus 2, and maybe some white noises. So that's the auto model. So if you want to do a auto model, then you want to follow the following steps. Okay, so you check ACF and PACF. To determine So you check ACF and the PACF of your raw data. And this raw data, not the raw data, it's a detrended raw data, okay, to determine P and Q in the ARMA PQ, just as what we did. And we will use that table to determine P and Q. And of course, here to determine P and Q is a not very easy process. So that is, you need to choose correct P and Q. By checking coefficients. BIC, residues. Just as what we did. So we checked the coefficients, whether the coefficients are significant or not significant. And then we also check whether the coefficients will make us a stationary process AR2 model. Okay. Yeah, so in the example I just gave, we do not check the AIC, BIC. We do not compare like this model with maybe other AR model or ARMA model. But in your analysis, I want you to do that in your like final project. Okay. And we also check the residual plots, and we hope that residual to follow a white noise. Okay. So this is the step if you want to do a auto model. And okay, let's first finish the second thing here. And if you want to cross model. So the cross model is that you use like other variables. You use like say X variables to predict Y variables or to find the relations between X variables and Y variables. So that's called like the cross variables. Okay. And if you like in your final project, if you want to do that, you will also basically follow the steps. Okay. So you check. So you first plot like those cross legs plot and determine which legs you want to include. Okay, so just remember, just recall like the SOI and the recruitment. We plot like the recruitment with like different legs of SOI, and we find that I think SOI 6 or SOI 7 has the largest correlation. So a good starting point is that we will first include SOI -6 in the model, and maybe we will also add SOI -7 in the model, and perhaps we'll also want to include some nonlinear terms in the model. So the first step is that you check your cross legs to determine which legs you want to include. Okay, and the second step is to, this is 2.1. Okay, and the second step is basically to choose the correct leg models. Choose correct legs by checking basically the same things here. The coefficients, AIC, BIC, the residuals. Okay. So you want to check the coefficients are significant or not significant. You want your AIC and BIC maybe to be the smallest in all the models you considered, and you want your residuals to follow a white noise process. Okay. right? So we will add more stuff like in this summary later as we like see more features in the time series. So we will see like how to add seasonality here. We will see how to add like the integrated model here. We'll also see how we can maybe check like the redundancy of the model here. So this is just like what I just write here is just a starting point of your final project. So you want to do all this in your final project, and I write it, I think, in more detail in the syllabus. So, but here I think since we just did a example, so I think it's just a good time to do this summary here. Okay, let me see. Yeah, and I want to see all this in your final project. Okay, so maybe any questions of this summary? Okay, so if there's no questions, I think now it might be a good time to do some theory stuff, to do some serious stuff of the ARMA model. Okay, so why? So this part we will basically talk about what ARMA model we want. So we know that we want a model need to be stationary, but it's not enough, and why we want the model to be stationary. And if there are other features of the ARMA model, so what are the features of those ARMA models? Okay, and remember that we have like that table to determine P and Q in the model. So why it is that table? So why we will use that table? So why that table is helpful? So in the theory part of like this ARMA model, so I will try to answer all these questions, and I will start with what ARMA model we want. So what's the features of the ARMA models we want? So we want it to be stationary. So we will start with stationary. Okay. ARMA model theories. So number one, stationary. And now call it stationary. So let's start with ARP model. Okay. And we want this model to be stationary. So the question is, so the question is, what restrictions we want to put on those coefficients phi in order to make this ARP model stationary? Okay. Yeah, so this is actually a hard question. I mean, a very hard question. So to make it easier, let's start with like AR1. Okay, so let's first consider AR1. So AR1. Okay, so AR1 is this. You'll realize that this is a hard question, but the answer is actually pretty simple. Okay, so the AR1 model. So this is an AR1 model. So we know its absolute value of phi is less than 1, then it is stationary. So this is from our previous class. Okay. And we can actually show. Yeah, I just give you the results and we can show by like the word decomposition. So by the word decomposition, we can show like this AR1 model actually can be written as an infinite sum of all the white noises. Okay, so which is this? And the coefficients in front of all the white noises is just like phi to the power j. Okay, so which is a very clean and a very nice result. Okay. So based on this, we can show first the expectation of xt is equal to 0, right? Because it is an infinite sum of the white noises, and the mean of the white noises is 0. So that means their summation should also be equal to 0. Okay. And you can also try yourself. Not actually, let me show you, this is actually not hard. Okay. You can also find like the covariance function. It's this, so which is does not depend on time. So we know here we see that the mean is 0 and the covariance is not dependent on time. So that suggests this AR1 process is stationary. Okay. So this is basically show that why this AR1 process is stationary. So AR1, we have studied AR1 a lot in early class. So now how about like AR2? So this is an AR2 model. So the question is that what restrictions we want to put on phi1 and phi2 in order for this AR2 model to be stationary. Okay, so like in the previous slides, I just give you some like 3 requirements on this phi1 and phi2, but actually there's a somewhat like more general theorem. Okay, so if the roots of like this function are both less than 1 in absolute values, then this AR2 process is stationary. Okay. So what is the root here? Okay, so if you remember from maybe your algebra class, so this is gonna be think I'm correct. Okay. Yeah, so these are the roots of this function. Okay, so here we have like two roots, right? Plus and minus. So if both of these roots are less than 1 in absolute value, so that is the absolute value of these two roots are both less than 1, then this AR1 process is stationary. Okay, and the corollary. So this condition is equivalent to what I just showed you earlier. So phi2 plus phi1 less than 1, phi2 minus phi1 less than 1. Yeah, you can show that this general condition is actually equivalent to this. Oh, yes, yes, yes. So that's the root, okay? So the root is basically the m that would make this equation hold, okay? So m is the, like the x or something, if you are more familiar with, yes. Maybe more clear. So what is a root? Root is the value of m that makes the equation hold. So that is a root. Okay. Yeah. And you can check yourself, or if you are not interested in this like root condition, or sometimes we call it like unit root condition, because it is less than 1, so we call it like unit root condition, is equivalent to this corollary. Okay. Okay. And just one more aside here. Is that we know that this unit roots can, these roots can actually have like complex numbers, okay? So if say like M1 or M2 is equal to A plus IB, so this I is the complex number. Okay. And if it is this, then we check. So then check A squared plus B squared. The square root of this is less than 1 because it's a complex number. We cannot like directly compare it with, so we just like compare like both the real part and the complex part. Okay. This is just an aside. So you might encounter those situations in your analysis. Okay. Yeah, so in your analysis, if you say, I want to use an AR2 model, yeah, and I perhaps want to say this, I want to say that your model is stationary. Okay, so let me finish the ARP model, the most general case. Okay, so the intuition, not intuition, or the motivation here is that we see that in the AR1, we want like this phi, the absolute value of this phi is less than 1. And here we want like the root of like this quadratic equation is less than 1. So in the linear case, like the root of that linear model is just phi1. Okay, but in here it's some combinations of phi1 and phi2. Okay, but the things that in common is that we want something of the model to be less than 1, or the absolute value of something of our like coefficients to be less than 1. So the motivation here is that is it also apply for the ARP model? Okay. So for the ARP model, do we also have like this so-called like the unit interval condition? Okay. So in AR1, AR2, the roots less than 1. And the answer is yes. So for in ARP, okay, So here is m to the power p. And this ARP is stationary. Okay. Yeah, but I mean, to find the roots of this like p order equation is much complicated than the quadratic equation or the cubic equation. So you want to ask like the computer to solve it for you. Okay, so there's perhaps like no closed form solutions for the roots of this like p order equations. Okay, but you can definitely find it if it exists. Okay. Okay, so that's the conclusion for a ARP model to be stationary. Okay. Okay. So next class we will talk about like what restrictions we want to put on the MA part of this ARMA model to make this ARMA model stationary. Okay, so I think that's it for today's class. I will see you next Monday.